So you're gonna learn about the quantum mechanics. So this word sounds quite scary, so we don't know what it is, but don't be scared. Yeah, actually, behind of this scary wording, the content itself is not very complicated. So the thing is, so far you learned about the macro scale physics, like this. So you learned about the motion of the object and the light, um, the optics, and also the what was the second part? So you learned about the Coulombic force and electric field, potential, and magnetic fields, like that. So they are all can be observed in our real life. So that's why we can call it as the physics in the macro scale. So for example, now you are seeing TV right here. Then for example, another example is we have the sand castle right here. And we have the fine gold bar. So they are all the bulk material and in the macro scale. But if you take a look, these object in the micro scale, then you can find totally different world. So if you take a look closely on this TV screen, then you can find these discrete the pixels with the different colors. So which is totally different from this nice image. This sand castle is consisted of the small sand particles right here. What about this gold? This fine gold is consists of atoms. So as technology is developed, eventually we could observe atoms, or we could sense some signals coming from atoms. So then the quantum physics has been started. So now we know these all the materials are consist of the atoms. Then if you do the examination, the experiment with these atoms, we found that very odd phenomena we never been expected before in this macro scale, which is we cannot explain those phenomena using the classical physics. Then we notice that, in this atomic scale, micro scale, we have a different world. Then we need to develop the new model to explain that. Then the most noticeable observation is in this atomic scale, the quantities are discrete. So in particular, the energy level of the electron in atoms is discrete. Okay, in real world, let's see. Okay, we have this object. Then it has a certain mass, and on the ground, if you put it here, its potential energy is 0. But if you lift it, its potential energy is increased for the gravity, right? And then if you drop it, then this potential energy is converted to the kinetic energy. Then about the level of this potential energy. If I lift it, then its potential energy is gradually increased for the gravity. It is continuous. That is the classical physics. But in the atomic scale, its energy level of the especially electron, is not continuous, and their energy level is discrete. So that is the key feature of the quantum mechanics. Okay, then let's think about. Okay, let me tell you what this quantum mechanics has been done so far. So basically, the main goal of the quantum mechanics was to understand how the atom looks like and how is the electron. So about 200 years ago, yes, we knew that all the materials consists of atoms. But at the time, we thought that atom is like just stone, solid ball right here. After 100 years later, yes, we eventually found that there is electron in the atoms. So this atom consists of the positive charged one and negative charged one, but they are mixed. So it is called as a pudding model. And after several years later, yes, we found that, okay, the atom has positive charged one and negative charged electron, but their position is like this. So at the center of the atom, we have a positive charges, and then the negative electrons are located at the boundary, outer boundary of the atoms. All right, so in this class, our quantum mechanics is starting from this moment. So we assume that we already know the atoms consist of nucleus, the positive charged nucleus, and electrons. Then we did various experiments to understand how these electrons behaves and what is the energy level of the electrons. And then eventually, after many kind of experiment and modeling, so Niels Bohr could make this model, the orbiting electron around the nucleus, like our solar system. But the interesting part is these electrons has the fixed energy level, discrete energy level, and these electrons only can exist on that given energy levels. And after that, Schrödinger mathematically derived the position of the electrons. So he suggested the electrons are existing as a form of cloud with a certain probability instead of the orbiting around the nucleus. Okay, so this quantum mechanics developed the new model of the atoms, and a lot of physicists verified whether that model is valid or not. And so far, the most recent the model of the atom is like this, the cloud of the electrons around the nucleus. And then this model is working well so far. Then you may wonder why we need to understand atoms and electrons. Okay, let me give you an example. Again, all the material is consisting of atoms. So of course, in the macro scale world, we don't have to care about atoms, right? Because the bulk, solid or gas, liquid, any bulk material in macro scale is following the classical mechanics very well. However, as the devices, sometimes we need a nanoscale or microscale devices. So even you are using the laptop computer, they are made of the semiconducting devices. They have the nanoscale features inside of the chip. Then in that case, we need to understand how the atom is working. Okay, all the material is consisted of atom here. Then these atoms has bonding each other. Then eventually they form this kind of crystal structure. And then they form this bulk material. So if you have understanding of these atoms, and you can explain and also can make a model of the bonding between atoms, then you can understand crystal structure. Eventually, you can understand the origin of these various material properties. So that's why we need to learn this quantum mechanics, especially how this atomic scale world is working. So if you have such understanding, actually this quantum mechanics is already applied in various fields like semiconductors and optoelectronics, like LED or the image capturing devices, and even lasers. In particular, from the next semester, you're gonna learn about the semiconductor fundamentals, EE 2003. So in this course, yeah, you'll use this quantum mechanics a lot. So actually, the quantum mechanics is simple. The atom is consists of the nucleus and electrons. Then, if you have a good understanding how the electrons are behaving inside of atom, then yes, you can smoothly start this course EE 2003. Okay, then let's talk about the atomic scale. So during 3 weeks, you're gonna learn about the various experiment and the various model about the quantum mechanics, especially about the atoms. Then most of contents are categorized by these two things. Number one, in atomic scale, yes, we do some experiment, but we cannot explain that behavior, that observation with classic physics, like a black body radiation, photoelectric effect, then sharp spectrum from atoms. Then today, so in this week, you already learned about this black body radiation and photoelectric effect, right? Then second, whether light or electrons are wave or particles. So in the classic physics, we learned that light is wave, electromagnetic wave, and electron is particle. But yes, in atomic scale, as the detection technology is advanced, we notice that, light has wave characteristics sometimes, but sometimes light has particle characteristics. It is related with photoelectric effect. Electron is known as particle, but sometimes it is behaving as wave. So you're gonna learn these kind of things during 3 weeks. Okay, then today we have two topics. One is black body radiation. Actually, this experiment and modeling suggested the discrete energy level of the electron in the atoms. The next, photoelectric effect. So this photoelectric effect explained the light is behaving as a particle as well, not only the wave. Okay, then let me ask you one question using the poll mode. Okay, so please pick the right answer. So number one, discrete energy model is suggested, then black body radiation proved it. This experiment proved this model. This the selection one. Second, black body radiation is measured. So we did experiment, and then discrete energy model explained it. So which one is correct? So we have 65 students in here. So I want to have at least 60 responses. It's getting close. All right. So the most of you selected the right answer. Okay, the answer is the second one. So we tested this black body radiation and then measured the spectral intensity for the wavelengths. And then we observed unexpected results which cannot be explained by classic physics. And then a lot of people try to explain that behavior using various models, and eventually Planck, yes, suggested this discrete energy model. Then he could explain the measured curve of the spectral intensity very well. Okay, so most of the model, the items in this quantum mechanics class has a similar history. So we do the experiment first, then we observe unexpected result. Then the physicists try to develop the model to explain that. Okay, so this is what the quantum mechanics is happening in history. So we are exploring atomic scale nature. It's totally different from the macro scale. So experiment result in the atomic scale contradict to the classical physics. Then physicists trying to explain with better model for their observation. And after that, after suggesting model, a lot of physicists try to prove it, or they try to prove it is correct or not. So the following experiment verified the model or theory. Then they worked well so far. But if somebody do the different experiment and found the observed unexpected result again, then who knows? We need to suggest another model. So that's the modern physics. Okay, the last one. It is hard to answer why. Because so far, we do the experiment, then we got unexpected result. Then we just developed a model to explain that. But we don't know why we have this atomic scale has such behavior. So it is like why F equals ma in the classic physics. So we defined this experiment by the experiment, but we cannot explain why. So please keep in mind this for the quantum mechanics study, the class. Okay, then let's start the black body radiation. Okay, so we all know that if the object has certain temperature, it emits the light. Sometimes if the temperature is low, it emits the infrared light. If the temperature is very high, it starts to emit the visible light. And then the color turns to red, to the blue, and eventually, if temperature is even higher, then it starts to emit UV light or even light with a shorter wavelength. Then, so about 100 years ago, when physicists tested the black body radiation. So we have the hollow sphere right here, then increase the temperature and maintain the constant temperature after heating up. Then the surface will start to emit certain light. Then we made a pinhole, then observe the light intensity for the wavelengths. So we attach the monochromator to collect the desired wavelength and measure the power of it. And then this is the result. So this is the wavelength, and this is the intensity, or sometimes you can call it as a spectral intensity, because each point is the intensity for the specific wavelength. So from this curve, at first, we have two key observations. The one is, if temperature is increased, the total power of emission is increased. What is total power in this graph? This area of the curve is the total power. Okay, then Stefan Boltzmann made a model, and they defined one mathematical equation to show the relationship between the intensity, the total power for the unit area, which is the intensity. Intensity is proportional to the temperature power of 4. So that means if you increase the temperature, this area of the curve increase proportional to the power of 4 of the temperature. Okay, so this is called as Stefan Boltzmann law. Then second key observation is there is the peak of the curve. Then as you increase the temperature, the wavelength of the peak, so we call it as lambda max. Lambda max is decreased. Then the Wien found that this change of the wavelength is proportional, inversely proportional to the temperature. So he defined this displacement law, the lambda max times t equals constant. So these two laws are based on the experimental observation, and they try to make the mathematical model to explain, to represent this behavior. Okay, then next. Beside of these two key observations, what is the meaning of this shape of the curve? So physicists try to explain why there's a sudden increase and then decrease after lambda max. So they try to make a model to explain that. Okay, at first, Rayleigh-Jean's law made this mathematical model, and Wien also suggested one model, but actually this model is working well at the longer wavelengths right here, but it is not well matched at the shorter wavelength region. And then Planck suggested this more complicated mathematical model. Then it is well matched with this experimental result. Okay, then what is his model? At first, he made very important assumption. The oscillating atoms, molecules, can have only discrete value of the energy given by here. So the energy level En is NHF. So HF is photon energy, right? Then it is increased by the integers 0, 1, 2, 3. Okay, so in here we have the discrete value of the energy level. So if you have a certain energy level, the electron cannot have the energy level in between them. Okay, the second assumption, the atoms and molecules emit or absorb energy in discrete packet. so-called photons by jumping from one quantum state to another. So this is the example. All right, so we have these two discrete energy levels. The lower one is NHF, and the next one is, of course, N+1 HF. Then electron can have only these two discrete energy level. Let's imagine the electron was at this higher energy level, N+1 HF. And then for some reason, this electron relaxed to the lower energy level, and then it emits the energy between these two levels, so which is HF. So that means when electron relaxed to the lower energy level, it released energy as a form of a photon right here. Okay, then next, in opposite way, so electron was here, the lower energy level, and then you shine the light, then electron can observe this photon energy. Then it can be excited to the next energy level. So we can have this reversible process. Then, how can these two assumptions explain the Planck's law? Okay, so this red curve is our observation. So this y-axis is intensity, the spectral intensity, and x-axis is wavelength. And then we observe that the intensity is increased to lambda max right here, and then gradually decreased as wavelength is increased. Okay, this is what we observed in the experiment. Okay, then how can this Planck's assumption explain this behavior? Okay, then let's think about this shorter wavelength region. In here, we need to consider energy of the photon and the probability. So in the shorter wavelengths, we have the relatively larger energy gap. Since this gap is large, there's a less chance to be excited or release the energy. So there is a low probability of the transition of the energy level of the electron between these two discrete energy levels. Okay, then let's consider this longer wavelengths. Longer wavelengths has low energy gap. So if wavelength is longer, the photon energy is smaller. So it has a more narrow gap of the discrete energy level. That means it has large probability of the transition. Since the energy level gap is narrow, it is much easier to have a transit compared to this large energy gap. Okay, then you can draw two curves. The one is for probability, the purple one. So as wavelength is increased, there is an increase of the probability of the transition. Next, energy. As increase of the wavelength, the photon energy is decreased. Then this intensity, spectral intensity, is determined by the combination of this probability and energy. So at very short wavelength range, its energy is very large, but this probability is too small. At very long wavelengths, its probability is very high, energy is too small. So at certain optimal point, you can have the maximum intensity. So this is how the Planck's two assumption can explain this behavior of the spectral intensity. So considering this assumption, he developed this mathematical definition, the formula. So in here, actually this term is the probability of the transition. Okay, this is how the Planck's model can explain the observation of this black body radiation using the discrete energy of the electron. Okay, then let's try some examples. Question number 1. A surface of the black body with an area of the 1 square centimeter has a total radiation power of the 20 watt. Determine, number 1, the surface temperature. Number 2, lambda max. Number 3, the radiation power with a wavelength window of the 1 nanometer around lambda max. Number 4, the number of photons per second escaping the black body in the wavelength window. Okay, so it's the surface area of the black body S is 1 square centimeter. Then of course, since it has a black body radiation, the spectral intensity curve will be like this. Then at this peak, you can define lambda max. Okay, then question number 1, we want to find surface temperature. Okay, then let me ask you one question. So which law is used for the relationship between light intensity, the total power, and the temperature, surface temperature? So I believe you can quickly give the answer. All right, very good, very good. The answer is the Stefan Boltzmann's law. The next question is, this is for the second question, lambda max. You have a temperature of the black body. Which law determines maximum wavelength, lambda max? All right, very good. So you need to use Wien's displacement law to find the lambda max. So this is how you can find the answer for the question number 1 and 2. Number 1, surface temperature can be determined by Stefan Boltzmann law. So in this question, you have a total radiation power, which is 20 watt. So the power is intensity times surface area. So the intensity is P, the power divided by surface area, which is 20 over 1 cubic centimeter. So intensity is 2 times 10 to the power of 5 watt per square meter. Okay, then let's use Stefan Boltzmann's law. I equals sigma T power of 4. Then what is T? T is I over sigma power of quarter, 1 over 4. So I is here, then this is constant. Then you can calculate the temperature, which is 1370 Kelvin. Remember, the unit is Kelvin. Okay, now we got the temperature of the surface. Then next, you can find this lambda max when you have the temperature of the surface using this Wien's displacement law. So lambda max is this Wien's constant divided by temperature. So the lambda max is 2.12 10 to the negative 6 meter. Okay, then let's move on to the next question. So it is quite similar with the one of tutorial question in this week. The radiation power with a wavelength window of the 1 nanometer around lambda max right here can be determined using Planck's law. Oh, sorry, this is typo. Okay, then you can use this spectral intensity using the Planck's law. Then the power, the radiation power, when the lambda max, in the range of the lambda max to the lambda max plus delta lambda. Delta lambda is 1 nanometer in this question. Equals the spectral intensity times surface area times delta lambda, which is the area of this rectangular. So to have a precise calculation, actually you need to do the integration. If the range of the wavelength is very wide, then you need to do the integration. But in here, the gap, the width of the rectangular is only 1 nanometer. So you can assume that this area between lambda max and lambda max plus delta lambda is the area of this rectangular. Okay, then as the area is 1 square centimeter and delta lambda is 1 nanometer, then we can bring this equation to here. Then let's put the numbers. So 2, this is pi, and this is the speed of the light. This is the Planck constant for this term. And okay, we already calculated lambda max in the previous question, right here. And then next term, S is area, 1 square centimeter. Delta lambda is 1 nanometer. So you need to convert the unit to meter. In the exponential term, inside of the exponential term, we have Planck constant, speed of the light, divided by lambda max, Boltzmann constant, and temperature. So the power is, total radiation power is 6.3 milliwatt. Okay, then question 4, the number of photons per second escaping the black body in wavelength window. So at first, we need to define the photon energy, the energy of the single photon, which is hc divided by lambda max. So you can calculate the photon energy. Then the number of photon per second is radiation power divided by photon energy. So the answer is 6.7, 10 to the power of 16 per second. All right, that was the example of, okay, we have one more example. So it was the past exam question. If the sun surface is treated as a black body and lambda max for the sun is measured as 0.5 micrometer, determine the temperature and radiation intensity of the sun surface. Yes, this question is more simple than the previous one. So now you have lambda max value right here. So if you use beam's displacement law, you can calculate temperature. So the temperature of the sun is the beam's constant divided by lambda max, which is 0.5 micrometer. So it is 5.8 10 to the 3, which is the 5,800 Kelvin. Then to calculate intensity, you can use Stefan Boltzmann's law. The intensity is sigma T power of 4. So this is the constant, Stefan Boltzmann constant, and temperature is right here. So the intensity is 6.4 10 to the 7 watt per square meter. Okay, then let's move on to the photoelectric effect. Okay, so from this photoelectric effect, we could find the light is a particle. Then let me ask you the same question as the black body radiation. Okay, actually the answer is yes, the second one. Yes, so we did experiment and observed very unexpected result. And after that, Einstein developed a model to explain that. Okay, thank you for answering. So before we move on this photoelectric effect, so I got one question from the chatting window. Okay, so this is for the question number 3 right here. The question is the way for the question 1, 3, the wavelengths put into R right here is always the smaller one. Yes, this is very good point. To be precise, we have to apply the wavelength value in the middle of this rectangular. So that means you'd better apply the average value of lambda max and lambda max plus delta lambda. However, this range is very narrow, so we assume that this applying this lambda max doesn't make large difference. That's why we just applied lambda max. But yeah, to be more precise, yeah, we need to apply the average value. Okay, this is very good point. Thank you for asking. And I hope that is clarified. Okay, then let me move on to the photoelectric effect. Yes, then let me explain what we have observed in this experiment. Okay, in here we have a vacuum jar right here. Then we have a 2 electrode. Then we shine the light. Then between these 2 metal plates, we have a circuit to measure the current, and also we want to apply the voltage. In the meantime, we can measure the voltage as well between these 2 metal plate. Then what we found is the first one is very simple. Once you shine the light, you could observe the flow of the current. That means there is the flow of the electron between these two metal plates when you shine the light. And after that, yes, we can do more precise, detailed experiment by changing the factors, the parameters. Okay, at first, when you shine the light, you can get some current. If you increase the intensity of the light, current is increased. It is reasonable. Yeah, so it is totally expected one. However, the interesting part is here. So when you shine the light, electron flows from E to C. And now we apply the reverse bias to block the flow of the electron. So we apply the potential difference between these two electrodes. For example, if we apply positive potential here, electron has negative charge, right? So this positive metal plate attracts electron. This electron, if this electron cannot escape this metal plate, then it cannot reach to the counter metal electrode. That means current doesn't flow. Okay, so if you start to apply the opposite bias, current is decreased, then eventually current stops at all at certain voltage. That means at this potential, at this voltage, electron cannot reach to the counter electrode. Then you can say this E times this stopping voltage Vs, which is the potential energy, electric potential energy, equals to the kinetic energy of the electron when it escapes from this metal plate, when you shine the light. Then one key observation is this point. This maximum kinetic energy is not related with light intensity. So when you apply the constant wavelength, constant frequency of the light, whatever intensity you apply, stopping voltage is always same. It cannot be explained by classical physics. Second, there's no time interval between the light and photoelectrons. So regardless the intensity of the light, as soon as you shine the light, you can observe the current. So in classical physics, if the intensity is low, then we can expect that electron can accumulate the energy from the light. Then after spending some time, if the electron accumulate enough energy to escape metal, then we could observe the current. That was the expectation based on the classical physics knowledge. However, as soon as you apply the low intensity light, we could observe the current. And this Kmax, the maximum kinetic energy, is related with the frequency of the light. That means if you increase the photon energy, so in here I cannot say photon energy because we didn't developed the model yet. So if you increase the frequency of the light, this maximum kinetic energy is increased, which means if you increase the frequency of the light, the stopping voltage is increased as well. Then you can draw this curve. So when you change the intensity of the light, you couldn't change the stopping voltage. However, regardless the intensity of the light, if you change the frequency of the light, this stopping voltage is changed. The last key feature is if the frequency of the light is below certain critical frequency, you couldn't observe the current. So as soon as this frequency becomes smaller than this value, then current stops, regardless the intensity of the light. So in classical modeling, although the frequency is low, if you can accumulate the energy in the electron, we believe that we expected electron can escape metal, but it wasn't. So expectation was totally wrong, which means it cannot be explained by classical physics. So, okay. So this is the last key point for this. So this is the frequency of the incident light, and this is the stopping potential. So if you increase the frequency of the light, the stopping voltage is increased as well, like this. And then at cutoff frequency F0, if the frequency is below this F0, we couldn't observe the current. So these are what we found in this experiment. And then Einstein developed a model right here. Okay, in his model, light is not wave anymore. So light is stream of photons. Then all energy of the photon, single photon, if you have the single photon, let's say this is electron and this is photon. So the single photon, energy of the single photon only transfer to single electron, not the other one. Left side of the screen. Because of me? Or how about now? So you cannot see the left side of the screen. Is it better? All right. So the all energy of the photon goes to a single electron. Then what is the energy of the photon? Energy of the photon is HF. And then another assumption in this model is metal has work function. This work function is working as a barrier. So this barrier blocks the electron to escape this metal. Okay, then this diagram is most important in this photoelectric effect. If you digest this, yes, you understood photoelectric effect. So we have a metal here, then we shine the light. So depending on the frequency of the light, we have a different photon energy. Of course, if you increase frequency, you have a more larger larger photon energy. Okay, then there is a barrier, which is work function. So if the photon energy is smaller than this barrier, work function, electron cannot escape this metal. Then if the photon energy is larger than this barrier, the work function, the remained energy goes to the kinetic energy of the electron. So you need to think about the energy conservation. So the sum of the kinetic energy of the electron and the work function is photon energy, HL. So from here, you can define this equation of the photoelectric effect. The maximum kinetic energy of the electron equals to photon energy minus this work function. Then, how can you explain this model? How does this model can explain these four weird observations of the experiment? Okay, number one, intensity. So so once you have a photons, intensity of the light is determined by number of photons, not the energy level of the individual photons. So the light, this maximum kinetic energy is independent to the light intensity. But one thing you can find is if you increase the intensity of the light, you have more photons. That means you have more electrons escaped from the surface of the metal. So the current is increased. But although you have a large intensity of the light, you still have the same stopping voltage. That means you still have same maximum kinetic energy of the electron. Because single photon provide energy to the single electron. Okay, then next. Of course, there's no time interval. As soon as single photon hit the single electron, it can escape the metal surface. And frequency. If you increase the frequency of the light, that means the photon energy is increased, but the work function is constant. Then what happens to the maximum kinetic energy? Yes, if you increase frequency, this maximum kinetic energy is increased as well. Okay, the last one. There is a cutoff frequency, and the frequency is less than this cutoff frequency. There's no current at all. There's no photocurrent. This work function can explain this. If the photon energy is less than work function, there's no photoelectron. As soon as this photon energy exceeded this work function, we can observe these photoelectrons. So this simple equation, yes, explains these key observations of the experiment, considering light is the stream of the photons. This is the photoelectric effect. Okay, and then let's try this example. This is a past exam question. In a photoelectric effect experiment, a metal is illuminated with light of the different wavelengths, and the stopping potentials of the photoelectrons are measured as a function of the frequency of the light, as shown below, right here. So we applied the various frequency of the light, and then measured the stopping voltage right here. Then they have the linear relationship right here. The first and second numbers associated with each data point are frequency of the light measured in unit of hertz and the stopping potential measured in unit of volt. So there are two numbers set. The first one is frequency, second one is stopping voltage. Okay, then number one, from the data given, find the value of the Planck constant. Okay, then now you can use the photoelectric effect equation. So in here, the maximum kinetic energy of the electron is equals to the charge of the electron times stopping voltage, which is the potential, electric potential energy of this metal surface. Then it is equals to photon energy minus this work function. Okay, then let's pick these 2 points, the first one and the last one. For the first one, the applied voltage is 1.7 volt, Vs is 1.7 times Q equals, the frequency is 1.5 times the 15. H minus work function. The last point, the applied voltage is 12 volt, and the frequency is 4 times the 15. Okay, so we have these two equations. Then we want to, okay, let's keep these two equations right here. We want to find Planck constant H. Then let's subtract these two equations. Then you can remove this work function term. So 1.7 minus 12 times Q equals 1.5 minus 4.0 10 to the 15 H. So Q is charge of the electron, 1.6 10 to the negative 19. So you can find the Planck constant, which is the slope of this line. So it is 6.6 10 to the negative 34 joules second. Okay, then next we want to find, what was the question? Determine the cutoff frequency and work function of this metal. Okay, so let's find the work function first. So we have, in this equation, so you can bring either equation 1 or 2. Then we already have this Planck constant. Then yes, you can calculate this work function. So how did we get this? I'm sorry. So actually, if you just bring this one and apply Planck constant and the charge of the electron, you can define work function. So which is 4.48 electron volt. And sometimes you can, this one use the drawing of this graph right here. So we draw the straight line crossing these dots. Then so you can define the work function right here on the y-axis. Then in the meantime, you can find the cutoff frequency. Of course, you can do the mathematical calculation. So if you have the work function right here, the cutoff frequency is work function divided by this Planck constant. So it is the 1.09 10 to the 15 hertz. Okay, then let's move on. The last question, a metal surface is illuminated with light of the wavelength 300 nanometer. The work function for the metal is 3.0 electron volt. Determine Number 1, the maximum kinetic energy of the photoelectrons. And number 2, the cutoff wavelengths for the metal. Okay, number 1, the maximum kinetic energy of a photoelectron can be determined by Einstein's model. So the maximum cutoff voltage. So if you cannot remember this well, okay, so think about this diagram. So we have a work function here, and this is the photon energy. The difference of them, the remained photon energy is maximum kinetic energy. So Kmax equals photon energy HF minus work function. Then in here, we have wavelengths of the light instead of the frequency. So this frequency turn to speed of the light divided by wavelength, c over lambda. Then let's put the numbers. This is the Planck constant, speed of the light, and this is the wavelength. Of course, you need to convert unit to meter. And this is the charge of the electron, because we want to convert unit to electron volt. Then work function is 3.0. So the maximum kinetic energy is 1.1 electron volt. And number 2, the cutoff wavelengths for the metal can be determined from the work function of the metal. So the HFC, the cutoff frequency, equals work function. Then this FC is C over lambda C. So lambda C is HC divided by work function. This is a Planck constant, speed of light. Then work function is given in this question, 3.0. And remember, the unit has been converted to joule. So you need to multiply charge of the electrons right here. So the wavelength is 4.1 times 10 to the negative 7 meter. So this is the answer of this example question. So, okay, in the previous question, I will change the solutions, then I will update this lecture note in the NTU-Learn website again. And also, I will add 2 more extra questions in the lecture notes. So if you are interested, please try them. All right, this is all for today. So yeah, again, don't forget to watch the lecture video before you come to summary lecture, and also before you go to the tutorial class. All right, thank you so much for your participation. I hope to see you again in the next week. Okay, thank you for joining.